Good morning. In this video, I'll be talking about equation of continuity. The equation of continuity is based on the ideal fluid. What does the fluid means? The fluid means that it is either liquid or gas. Liquid or gas we call as the fluid. And the ideal fluid means it must have the steady flow. So let me explain this one. Let us consider a tube here, and through this tube some fluid is flowing through this one. And when it is ideal fluid, then at any point the velocity, the pressure does not fluctuate at the time. That means if you measure the velocity at this point, now let's say at time equals to 0 second, then after time equals to 10 second, the velocity would remain constant. That is, it is not fluctuating with the time. Not only the velocity, the pressure as well does not fluctuate with the time. And the streamline means the fluid passing through this tube has a well-defined path. That means it moves along a smooth continuous path here, and this smooth continuous path we call as a streamline, and these two streamlines never cross each other. If they cross each other, then the fluid will not be smooth, rather it will be a turbulent flow. And for equation of continuity and for Bernoulli's principle or Bernoulli's equation, we do not want to be the turbulent flow, because these are based on the conservation of energy. Energy will no longer be conserved. Okay, so for this assumption too, we need the streamline flow. And now next thing is non-viscous. That means non-viscous means the fluid has no internal friction. That is, there is no any retarding force. Okay, and this is also required because if there is any friction, then the sum of the energy will be lost in the form of heat energy, and the equation of continuity and Bernoulli's principle will no longer be valid. And then last one is incompressible liquid. That means the density of the fluid does not change regardless of pressure change. The pressure changes from point 1 to point B, but the density does not change. That we call as an incompressible liquid. Okay, so this is the ideal fluid. Now let's talk about the derivation of equation of continuity here. So here we have chosen a tube here, and then we have considered a very small length here, and let's call the volume in this area, in this tiny segment, the delta x1 is a v1. And remember, this capital V stands for the volume, and this curly V stands for the velocity. So make sure that you understand these two terms correctly. Okay, the capital V means the volume, and the smaller or italic V means the velocity. So what does the equation of continuity tell you? That the mass flow rate at any point must remain constant for the ideal fluid. The mass flow rate. That means the dm over dt at any point must remain exactly the same. It does not change here. It does not change. So that's exactly what I have written here. Mass flow rate is constant. That means dm1 over dm2 must remain constant. What does dm1 means? The dm1 means the mass of the fluid in this tiny volume here, and m2 here means the mass of the fluid in this tiny volume here. And if you can recall, the density is equal to the mass per unit of volume. So if I have to write down in terms of mass, it will be density times volume. So that's what I have written here. Instead of mass, now I'm writing down the density into the volume here. Okay, and the same thing here. The mass m2 is equal to rho 2 times the v2, and rho is the density. Remember, rho is the density, and this v is the volume. And now the volume, if you look at if you have to find the volume of this tiny portion here, then the volume would be equal to area times the cross section. Sorry, the cross volume is equal to cross section area times the length, and that's this length here. Okay, and over this length we have chosen so tiny segment that over this length the cross-section area does not change. Okay, so I have written down the volume is equal to the cross-section area, and this length is delta x1, and simply the delta x1 means it's a very tiny segment here. And the same thing here for the V2, A2, because the cross-section area here is A2 times the delta x2, which is the tiny segment here. And now if you look at the density and the cross-section area here, it does not fluctuate with time. It's a time independent function, so I'm taking it out, because as the time passes by, the density and the cross-section area does not changes, so I'm taking it out. The same thing on the other side. So now we have the term, the dt over delta x1, and on the other side we have d over dt and delta x2. And this term, what does this term means? It is the position changes with respect to the time, and that we call as the velocity of the fluid. And this velocity is v1. Remember, the instantaneous velocity is equal to v equals to dx over dt. Rate of change of position we call as the velocity. That's what it is here. So this is the velocity of the fluid at this point, and this is the velocity, v2 is the velocity of the fluid at this point. So we have this equation here. So in this equation, this equation tells you the density might change from 0.1 to 0.2 here. But if we're considering the incompressible fluid, then rho 1 and rho 2, that is the density does not changes from point 1 to point B. So that will be the most cases in this talk here. So rho 1 and rho 2 remains constant, because here we're assuming the density is not changing, or it is an incompressible liquid. So we now get an equation A1 V1 is equal to AT V2. Okay. So remember, A1 V1 is equal to A2 V2. What does this mean? That means if you look at the cross-section area, if cross-section area A2 increases, then V2 must get down. Or if A2 gets down, if A2 is smaller, then the V2 must be faster. That means the fluid must move faster where the cross-sectional area is smaller. And you might have experienced these things when you water a garden with a water hose. If you press the water hose with your thumb, then the fluid moves faster, and the reason is the cross-section area has reduced. If the cross-section area reduces, then the velocity becomes greater. So now I'm trying to explain this one in the streamlined way. So here we have a fluid that is passing through this pipe here, and this represents the streamlines, and here the area has reduced. So when the area has reduced, the more streamline passes through this narrow area here. So if you simply look at the streamline, when the streamlines are closely packed, that means the velocity must be greater there. When the streamlines are closely packed, the velocity must be greater in comparison with this one. If you look at this one and this one, clearly the area has reduced, and also the streamlines are closely packed to each other. That means the velocity has increased. Okay, so now there's another example here. When you open the faucet, then you might have seen the water is getting tapered along this direction here. Why does it happen? It happens because as the water is flowing down, the velocity starts increasing. And as the velocity starts increasing, remember this equation, A1 V1 is equal to A2 V2. As the velocity starts increasing, what should happen to the cross-section area? It must go down. So it is getting down. Okay, and now there will be a point where the cross-section area becomes so tiny, then it will no longer be a streamline flow, then it will be a turbulent flow. And you will see, like after a certain point, the liquid flow will be most like a droplet, or it will be turbulent flow. So as far as the flow is streamlined or laminar, and as the velocity increases, the flow diameter gets thinner and thinner. So this is it from the equation of continuity. In the next video, I'll be talking about the Bernoulli's principle. Thank you very much.